Our next speaker is Jaimin, who will be talking about Libcamera and AOSP.
Yeah. Yeah. Hi all. Myself, Jaimin Parmar. I am working as a senior software engineer at TechMahindra. So basically, today we are looking into one of the open source Libcamera stack and how it will be potentially the next camera HAL for the AOSP. What today we are going to cover is this uh, open source sleep camera, their full stack, and how it can be integrated into the Android, and some debugging hooks if you are planning to bring up this sleep camera into your custom SoC. Okay. So when we talk about the camera, basically, so when just we think about the camera, what comes into the mind? So basically, has the, let's see, many of you has developed the V4L2 camera app. So basically, V4L2 camera app directly talks with the kernel drivers, and basically that will leverage the hardware capabilities, and you will get your images. So if we talk about the V4L2 camera app flow, so this is a very simple and generic flow V4L2 camera app will follow. So first thing is it will query the capabilities. So based on the capabilities, it will set formats, and after setting the formats using the V4L2 IOCTL calls, it will request for the buffers. It may be the DMA buffers, or it might be software buffers, and then you have to the queue the buffers, and after queuing the buffers, you can start the stream, and the cycle of the queuing and dequeuing goes on unto the stop stream. Okay, so basically when you have the simple camera hardware, everything goes right. But let's see, the things change now. So how this modern camera basically looks like. Basically, so whatever the parts you are seeing in slides, basically in the right of the dotted red lines, it is basically inside one SoC. Okay, so basically whatever you are seeing, the black correction, defective pixels, I2C controller, CSI5, so it is inside one of the SoC, and these are the hardware blocks. And if you seeing, okay, the left side of the dotted lines is the camera sensor, external camera sensors. So let's just, okay, move through the how this modern camera basically, okay, works and looks like. So camera sensor basically has a control unit over the I2C bus, and you can send instructions to the camera sensors. And whenever the data comes, so data basically comes over the CSI2 pipeline, and it has a CSI5 basically data handle, and based on the bus, it will go to the your black level. So these are the basically the ISP blocks, image signal processor blocks. Okay, so this is the very generic and typical flow. So basically means if you took the real hardware, it goes complex, but this is just to understand, okay, how the camera pipeline works. How took this. So basically once your maybe the raw image or the bare sensor image comes, it will go to the black correction. So basically sensors have the dark current. So basically if you have the black pixel also, then it will draw some currents. So okay, to minimize that, and basically it has some offset, okay, to get the correct pixel value, we have the black level correction. Then it comes to the defective pixel correction ISP blocks. So basically what defective pixel correction ISP blocks do is, at the time of the manufacturing, some of the pixels are defective. to correct that defective pixels, we have the defective pixel correction. And basically what are the defective pixel correction are stored under the some of the non volatile memory, okay, where from you can take okay, what are the non pixel defective pixels, and you can correct it. Then it will go to the demosaic, where you can convert to the RGB, and it will go to the color correction, where you can naturalize and adding the more colors. And after that it will go to the scaling, where the downscaling will happen. So basically these are the okay, how the modern camera basically looks like, right? So let's see, if we want to okay go one slide back and wants to control this from the camera app, right? So it will be very difficult too, because these are the different ISP blocks, and you have to connect the each blocks. So basically if you see CSI5 black correction lever, so to control from the kernel layer we have the media controller, we have the V4L2 and media controller APIs. So every block has the seeds, every block we will call it entities, and every block has a source and a sync pad. So basically if you see the camera sensor, right, so it has a source pad only. So we will call it the source pad, means it is giving you the output only, and it is coming with the CSI. So here we will call it the sync pad, and again it is sourcing like this comes, right? So basically here when you okay come to a modern camera, you have to make the pipeline to get the correct result. Okay, so basically let's see, if everything comes to the application layer, right, application developers has to more aware about how your hardware looks like, and it will be difficult. So this is a OMAP 3 camera in Nokia, and you can see how complex the camera pipeline will looks like. Okay, okay, to ease the basically this means to don't have the camera app developer don't have to more aware about the how the hardware underlying hardware works. Here comes the Libcamera. So what is the Libcamera? So Libcamera is a complex camera support library, and it is basically supports the Linux, Android, and Chrome OS. Sorry. And the Libcamera, what is and why we have the Libcamera? So first thing is Libcamera is the open source, and it is driven by the Linux media community, and it has and why? So basically it is a full user space stack. Okay. So basically it does not contain anything related to the kernel. So here we are not talking anything about the kernel. And if you want to okay make your SoC compatible with the Libcamera, you must have the media controller drivers upstream, so that will leverage the capability of the media controller APIs, and Libcamera will talk with it. And so basically when it comes to the camera HAL in the AOSP, so most of the OEMs don't give their camera basically source code. They are all the proprietaries, right? Because there is the image processing algorithm implemented. So Libcamera also gives okay vendor specific closed source IPA implementation integration. So we'll look into the more details in the architecture. And it has a reference implementation for the Raspberry Pi also, and Intel IPU 3 and Rock chips. And basically it will give us Android OS of wrapper HAL, so you can directly integrate it with the Android once your pipeline is up. So Libcamera is nothing but one towards the adaptable layer for the camera integration. Okay, so this is the how camera stack looks like. This is a Libcamera stack. So on the top we have this adaptation layer. Here the adaptation layer, and we have the application layer. So basically application will talk with the adaptation layer, or application will directly also call the Libcamera also APIs, right? And if you talk about the Android camera framework, so basically the in the Android camera framework at the top we have the applications, and then it will go to the camera HAL, and basically this HAL will load the Libcamera. Has the Libcamera has a plugin, and Libcamera will take care of the all the your hardware specific kernel drivers. So let's a little bit deep dive in the Libcamera architecture. So in the Libcamera, whatever these blocks you see here, so in the yellow are the device agnostic blocks. Okay, whatever the means, it doesn't depends on the your underlying the hardware. And here you see the this a pipeline handle, right? The block in the green, basically this green. So this is the device dependent. So all your device based logics will be come here, and this IPA module, image processing algorithm, uh, basically this will be closed source also or the open source also. It based on the your implementation. So basically what comes in the pipeline handler. So basically what will a pipeline handler do? Let's see, if you have the complex ISP what I have shown earlier, and basically pipeline handler will uh, if you have more than ISP, then pipeline handler has implementation of the what are the different types of the ISP you are going to support. So basically there will be the match function, so that will match what are the ISPs your pipeline will handle. So basically in the one Libcamera you have the more than one pipeline handler also to handle the this ISPs, and it will this pipeline handler basically take cares of the your stream configurations also. Basically you have the stream configuration like the still camera, viewfinder, video recording, and and you can also the policy also like what are the best ISP output from which I can get the best video. So based on that you can do the configuration also, and based on the hardware in the pipeline handler, based on the hardware, let's see, this Libcamera will support the multiple stream also. So there you can configure how many max stream this my hardware will handle. That also you can configure also. And the logic for the loading the this IPA module means what are the what type of the IPA modules you want to load basically. Okay, maybe IPA module you can load has a one has a shared library also there, or it may be directly compiled with the Libcamera also, has a static library. And if you don't want and you just want to your IPA module has a like a closed source, so basically it will what this Libcamera architecture will do, this your IPA module won't run in the Libcamera process. It will fork the process and it will run in the sandbox. And the this communication between the this IPA module and the Libcamera is on the Mojo IPC, basically they are taken from the Chromium. And if we take a look at the core libraries, to implement the pipeline handler and the IPA module, so they have some core library where the camera configurations and the camera based like what is the capabilities of your camera. And let's see, if you have the IMX219, then what is the physical size of your camera. So that are all given as the camera sensor info. And after that there is the kernel and hardware. Okay. So basically this is the how the structure of the Libcamera looks like, source structure of the Libcamera. It has a this is the build directory. So basically it will generate once you have the run the build commands. It doesn't come with the git tree. So there is a documentation. You can find the documentation guide, include headers, and full implementation of the source you can find inside the source code. I'm not going to get more deeper into it. And here in the Android we have the AOSP HAL wrapper, just to get compatible with the AOSP HAL. And in the IPA we have the means algorithms, and they have already implemented for the IPv3 Raspberry Pi, VMC. It is a virtual, and Libcamera source, and they have the also language bindings. Okay, so you can develop your Python application on the top of the Libcamera. Okay. So basically what it takes to integrate it with the Android architecture. Okay, so basically this is the how the Android stack look like. So I'm not going to much deeper into it, but this is the, let's see, if you want to talk has a camera app. So there is a camera app, then there is a framework APIs, basically that API framework APIs, and we have the hardware abstraction layer. So basically this is the where our Libcamera comes into the action at the HAL layer. So basically this all are this camera app and the Java APIs are not going to change when we are integrating the Libcamera. Okay, so let's see. We will go through flow of the how the camera will work in the Android AOSP. Basically, I'm not going to cover here the camera app. So we will directly come with the camera service. So in the AOSP, the camera server basically it is started by the init process only. So here you can see this is a service camera server, system bin camera server. So this will be started at the boot time only by the init process, and this is how is the init RC file will looks like, and it will register. It has the AIDL interface. So basically the camera app and the underlying HAL will talk with this camera server using the AIDL. So once once the init process will start the camera service, there it also start the camera provider manager. So what basically this camera provider manager will do is, the camera provider manager responsible for finding how many camera HAL. So basically camera provider HAL is what will provide the camera device to your Android upper layer. So camera provider manager will launch and it will it will ask the system, okay, means how many camera provider managers we have, and it will register with the camera server. Okay, now we will go to the camera provider. So basically this is the big picture of the this camera provider. So this is the AIDL implementation of the camera provider. So I just want to show the libraries only. So in the camera provider, basically you have the one camera service which will be started by the init.rc init process only. And basically if you let's see, if you don't have the Libcamera, so full is implementation will be done in the .implementation.so file. So at the runtime only it will load .so file, and here whatever you can see in the last block, right, the camera.libcamera.so, libcamera.so, and libcamera base.so. So this is the where the Libcamera comes into action. So this camera provider basically calls the get hardware module, and it will load the this camera.libcamera.so files. This is where the Libcamera init process and the main architecture comes into the action. Okay, so now we will take a look into the Libcamera initialization flow. Okay, so basically once, let's see, your library is loaded by your Android HAL. So basically Libcamera is like a plug and play like a module. So you can directly if you have the camera provider HAL, you can directly call that SO library, and basically it will do the DL open, and you have to call the camera init, and this all the functionality of the camera init is in the source Android camera HAL manager.cpp. So this is the file from Libcamera git tree. So let's take a look. So basically in the this Android camera HAL 3 wrapper of the Libcamera. Okay, so the this will HAL module InfoSys. So it will you can see camera module APIs hardware, and if you come here, you can see the HAL init. So basically this is the init function. This init function was called by your camera provider HAL only, and initialization will take place. So this is the HAL init process, and it eventually initialize the camera HAL manager, and it will call the HAL instance init. And this is the how the after once you call the init, so it will start the camera manager. So this is the camera manager from the Libcamera, and once you call, then this a device enumeration will happen. So what it will do is the Libcamera itself will go to the if you have the UDEV based device, so it will go to the UDEV's rows, and it will try to find out what are the media devices you have. And if you don't have the UDEV, it will also go to the sysfs media, and it will try to find out all the media devices. Once it has all the media devices, then basically it will try to get its entities and capabilities of the ISPs. Once it will get the capability of the ISP's name of the entities, it will call basically this create handlers. So basically what this create handlers will do is create handlers will get all the available pipeline handlers available in your Libcamera, and one by one in the pipeline handlers you must have the one match function. So it will match ISP entity's name with your pipeline handler. If it's match with your pipeline handler, means your pipeline handler will able to handle the ISP, and eventually it will call the add camera, and add camera basically emits the signal. So it emits the signal, and it will go to the upper layer where we have initialized our camera HAL 3 wrapper. Okay, once this camera add emit signals goes, then it will call the camera add, and for the AOSP they have the configurations file. So in the configurations file you can configure what are the means camera nodes you want to show into the upper layer, and basically the initialization process will take place, and it will also initialize all the capabilities of the camera. So if you take example of the camera 2 APIs in the Android, so it has so many capabilities. So let's see if your Libcamera architecture something missing one capabilities, then it will fail, and it does not initialize that camera node because it does not have the proper capabilities, right? And if everything goes right, then it will send one callback signal to the camera framework that one new camera node is added. Okay, so if everything goes right, then you can if you have enabled the debug logs, then you can see the camera ID added successfully. Okay, so basically this is the sum of means in the I've just discussed, right? So you have the camera HAL.yml file, so it will be read at the initialization only. So to get your camera position, like the front or back, or how much rotation you want. So basically, let's see, if you don't have this file, then your Libcamera will be initialized, but it doesn't show in the Android, because this is a very specific file to the Android, and you have to add all the properties. Okay, and you have to also define the location of the Libcamera, means Libcamera HAL. So this is just a course implement, and this is the slides we'll go through, and this is the camera capabilities where all the capabilities initialization will happen. So if anything is missing, you can add there. And this is just a build system, so it is using the Mason build system, and backend has the Ninja. This is the some of the commands, basically Mason setup build, okay, configure build, and you can also you have the choice to okay, what are the pipelines you want to build, and what are the applications you want to enable in the Libcamera. This is the build configuration, basically comes once you run the build command, and it will tell you okay, what are the options you have enabled. Okay, But here the what has the Android developer, the missing piece is the Android BP or the Android MK. So it is the Mason based build system, so it does not have the Android BP or the Android MK. So in the community from the long it is going, that means how to integrate this into the tree basically, because we cannot write the Android BP directly or Android MK, because it is some for the IS IPC communication for the Mojo, Libcamera will generate intermediate files at the build time, so that you have to hardcode into the Android BP. And basically this is what suggested by the this main architect Lauren Pichart. So this is the suggestion, okay, given by him. And okay, I just want to discuss some of the, let's see, if you want to bring up your SoC Libcamera in your SoC. So first thing is how to enable the locks, right? So basically really I spent 2 to 3 days just to enable the locks on the Android. So because if you saw in the documentation everywhere given, it is like you have means this is the environment. So if you run into the Linux command line, you can directly set the environment, and after you run the library, okay, it will take from the environment. But in the our Android, it is not the okay case. So basically in the whatever your RC file of your camera HAL camera provider HAL, there you have to mention what is the log level and what is the log file. And let's see, if you don't want to do this, basically what I have done is I have just hard coded the okay in the log file only, so to get rid of the every time okay means okay changing the provider. And to before coming to the very upper layer, if you want to let's see, if you are the pipeline handler, everything, if you want to just check how much camera Libcamera will work or not. So basically there is a cam tool already present in the Libcamera, you can build it. And if you run the cam -l, means it will list the what are the available cameras. And you can check your pipeline by cam -c1. So means it will capture from the camera 1 basically 10 frames, and it will dump to the file location. And after the dumping, if you want to check the camera, you can use the Fmpeg or some other tool, okay, to get the look into the pictures, means how your camera looks. Yeah. And from the Android point of view, I'm using the DumpSys media camera. So this is just a code snippet. So let's see if the Libcamera underlying works, but something goes wrong on the camera HAL. And it is not able to means add the camera at the HAL upper layer, means framework layer. So if you do the DumpSys, you can see here there is no camera. So it will show the what are the camera devices for the clients. So DumpSys is a very useful tool for the debugging. And in the DumpSys, you can see also basically what are the camera providers HALs which are registered with your camera server. Okay, so basically this is the code snippet for the failed scenario. And this is the code snippet I have dump for the success case. So here you can see that I have one camera. I have one the camera device. And if you see here, so basically we have the true providers, the external provider, and this is what my one Libcamera, and it has also one devices. So in the DumpSys also you can see the what are the active clients you have. If something wrong, something goes wrong at the application layer or framework layer, you can see in the DumpSys logs basically. Okay, so basically these are the references what I have used. And yeah, thanks.
Do we have any questions?
Can Libcamera also be used in Linux
Yeah, of
Android
course.
devices like post-market OS?
Yes, of course. of course. But basically, the Libcamera is like you must have the hardware support. Okay, you have to add the hardware support there.
Can this Libcamera also work on Qualcomm based platforms? Because I know that Qualcomm has their separate camera stack.
Yeah, so basically the Libcamera is basically what if you just okay consider these slides. So basically it will take the capability of the ISPs, means IFC. So if you know the underlying hardware, okay, ISP hardware of the Qualcomm camera, Qualcomm stack, and if you can add the support for that, then it will of course work. But yeah, for that you have to add the support.
It will be difficult as I believe that everything runs in library format in Qualcomm stack for ISPs.
Yeah, that's why we have the Libcamera, right? That's why we are going to try to add the support for the Mali C55 like that. Yeah.
I think one of the post-market OS devices. I think one of the post-market OS devices could be Pixel 3a or uh, yes, OnePlus 6T or something. So they have the camera working, and I think they use Libcamera. I may be wrong, but I think I just seen it last week or so. So because they are very excited to have the camera working. It's very difficult to get a camera working, especially on a production device where you don't know what CSI or CAMCC. CAMCC is the Qualcomm driver, whatever magic they are doing behind the scenes.
I think good talk for outside in hall.
Sure, definitely. Thank
Okay.
you.